Sí.
Do you understand me? Okay, that's good. Okay, 1 minute. I don't remember what we met the first time. Very, very happy.
Muchas gracias.
Okay. Well, buenas tardes a todos, bienvenidos. Es un placer para mí, pues, presentarles al doctor, al profesor Sowaila. Él es pues, es una persona que conozco desde hace muchísimos años. Él es profesor de la Universidad de Ohio y también pertenece a la división de nanociencia y tecnología del Laboratorio Nacional de Argón, ¿no? De Argón National Laboratory. El profesor Ha recibió su licenciatura con honores y su maestría en Yangon University en Mainar en 1990. Después realizó una estancia en el Instituto de Física Teórica de Trieste, en la parte de teoría de materia condensada en Italia en 1993, y en 1997 obtuvo un doctorado en física experimental en la Universidad de Ljubljana en Eslovenia. O sea que es totalmente multinacional aquí. Después realizó una estancia postdoctoral en el sincrotrón en Trieste, Electra, en Italia, y después estuvo en la Universidad Libre de Berlín y en el Instituto Paul Drude de electrónica de estado sólido en Berlín, en Alemania, del 1998 a 2001. El doctor La comenzó ya como profesor en la Universidad de Ohio en 2001, y en 2011 fue promovido como profesor, como full professor, ¿no? En este sentido. Él ha sido visitante de diferentes lugares, en particular del Departamento de Física Aplicada de la Universidad de Hamburgo en Alemania, de 2008 a 2009, y en el Departamento de Química de la Universidad Paul Sabatier en Toulouse, Francia, en 2010, donde ha realizado periodos sabáticos. Bueno, ha sido director del programa de materia condensada y superficies de la Universidad de Ohio. Varios de nosotros hemos estado ahí. Yo estuve hace muchísimos años, en 1995. Soy de las que con mayor antigüedad aquí. Después tal vez Francisco y después David y también Raúl, ¿no? Que ha de estar por ahí. Está entrando Raúl Esquivel por ahí. Bueno, y es el líder del grupo de materiales magnéticos y electrónicos y de dispositivos. Y del grupo, es que estoy traduciendo en tiempo real, de materiales cuánticos y de energía en el Laboratorio Nacional de Argón, donde él ha realizado y ha puesto en marcha y ha construido diferentes equipos, diferentes instrumentos. Y bueno, no voy a hablar más. He's a really, let me say that I'm very happy that you are here. And you know, I have been in touch with you a lot of time. We met almost every year, where we know about your progress, your wonderful and excellent work You have done a lot of instrumentation and a lot of physics around that. And today you will talk about quantum molecular machines in action. So let me thank you, and please go ahead. So thank you for being here.
Muchas gracias. Thank you very much for a very nice introduction. Excuse me that I have to speak in English. Let me see, I can put now my slides. Do you see the slides? See?
See? Yes, we do.
Yes. Do you also see the little translation underneath?
Yes, verlas diapositivas, yes.
So please forgive me if some of the words are wrong there, because it's a machine, but I will, when I speak, I will same time translate to the Spanish so that if you miss it, you can catch up with the language a little underneath.
Okay.
Thank you very much for invitation. Today, I want to explain to you about something that is with my heart. It's a little machines. Quantum, I call it a quantum machine, and I want to explain it and having some fun with this. So let me explain to you. My talk is organized. First, I'm going to introduce you a little bit long way about the atomic manipulation techniques. And then I will move on to molecular machines. I will give 4 topics: molecular motors, chiral molecular propellers, and then molecular motor network. And also, I will inform you about supramolecular nano car and our upcoming Nano Car Race next year, second Nano Car Race. So let me start with the basics. This is for the students, not meant for the scientists. So the scanning tunneling microscope that we call it is used a very sharp tip, and it's positioned about 1 nanometer or less distance from the surface that we want to investigate. And when we apply the bias, there is electron can tunnel. This has to be a conducting surface. And using that tunneling current, we can maintain the distance, and we can scan to get the images of the materials down to the atomic scales, so that we can see the atoms, we can see the molecules. Let me move this one. I'm sorry. We can see the molecules and so on. So I want to start this with a little bit of inspiration. Here, I borrow an image of the STM tip from the web. The typical aspect ratio of the STM tip is about 3:1. So 300 micrometer to 100 micrometer. Just for a comparison with, let's see, with the Eiffel Tower. So Eiffel Tower is also the same aspect ratio, 300 meter to 100 meter. So if you do a little math, Eiffel Tower is about 1 million times larger than an STM tip. So if we want to position the STM tip on the surface, we have to put about 1 nanometer distance, the tip. If you multiply with 1 million, you get 1 millimeter. So we need to position the Eiffel Tower 1 millimeter distance from the ground, and then we have to move it with 0.001 millimeter. So this is just for fun, just to explain. Of course, what we are going to do is that we work, okay, at the low temperature in ultra high vacuum environment, so atomically clean substrate. Today, I'm going to use gold and copper 111 substrates, and the temperature that I'm going to talk about is 5 K and 80 Kelvin. Those are the experimental conditions. Now, let me explain about the key techniques that I'm going to use to study these molecular machines. These are, we call it the manipulation technique. So the STM tip that I just explained, we can use not only to take the images, but also to manipulate the atoms and molecules. I will roughly divide 3 techniques. One, we use force, tip sample interaction force. We have to approach the tip closer to the atoms or molecule to do that. 2, we can use electrons. Those are the tunneling electrons. We can use inelastic electrons. Those are the captured by atoms or molecule to excite. Or we can simply use the electric field because we apply the bias. There is a polarity between the tip and the sample. So there is a local electric field. So I'm going to first explain in detail those techniques, and then I will move on using these techniques, how to study the machines. So the atom manipulation, if we want to move an atom, we need to approach the tip. Typically about the tip is like 6 to 7 angstrom above the surface if we are taking the image. But if we want to move the atoms, we have to approach the tip closer, like 2 to 3 angstrom away, and we move the tip. Typically, the atoms or molecule follow the tip in a stepwise manner. It's jumping step by step. This technique was first introduced by Don Eigler, in fact, 31 years ago, by writing the xenon atoms and writing IBM logo. Here's an example of the atom manipulation. What you are looking is the STM image of a silver cluster on silver 111 substrate. And we use the STM tip to pull out the atoms, one atom at a time, and then move these atoms to build a quantum coral or structures here. So these kind of manipulations. And another example, we can use that for the molecules. For example, in this work, we use the force manipulation to remove the molecules. What you are seeing here is a self-assembled buffering molecules, global buffering molecules on silver 111 substrate. And we remove the molecules to sculpture hexagonal structure here. So that's just simply the removing the molecules. And we want to study the properties of this hexagon we can create. Or in this case, what you see is a little hole we are filling with the atoms to fill back. So these are individual silver atoms. So this is, we call it the atomic manipulation. Okay, so the atomic manipulation is no longer very advanced because we have already tested with the little kids. In Ohio University in 2009, I made a public outreach and little kids who visited to our lab, and we asked them to move the atoms. So these are the kids, they were lining up, and each kid moved one atom. The project was a little atomic school bus. And this school bus will be the world's smallest atomic school bus. So what you are seeing here, these green little dots are individual atoms. And here it is the movie made by these little kids. There were 26 kids. They turn around and they move one atom at a time to create this little school bus. You will notice here that the atoms are not really round. It's because of the drift, but I can't complain to the kids. It is what it is. Okay, now the next technique I want to explain is called inelastic excitation. In this case, we are using the electrons not the interaction between the tip and the sample. When we tunnel the electrons on the molecule or the atom on a surface, electron normally pass through, tunnel through. However, by chance, an electron can be captured in the molecule. In that happen, we call it inelastic tunneling. Normal tunneling is elastic tunneling. Okay. If that happens, electron is captured in empty orbital of the molecule, then the energy is transferred to the molecule, and the molecule can be excited to rotate or to vibrate and so on. And we can control this process. And we can even count how many electrons are involved in the process using this equation. Here, R is the energy transfer rate, is proportional to I, that's the current, to the power N. N is the number of electrons that involve. So if we know the current, if we know the energy transfer time or the rate, we can find simply the number of tunneling electrons involved. So here is an example in 2006 that we have played around with a chlorophyll molecule. So this is the chlorophyll is the molecule that makes a green color in plant leaves. Here the molecule of single chlorophyll, and we inject the electrons to change the shape of the molecule. And again, we can change another shape and finally this shape. And we can control the process. And this looks like this. We are turning, in fact, the backbones of the chlorophyll tail. And the process can be controlled so that not only we know this is changed, we took the image. During the process, we record the current. As soon as the structure is changed, we know the change in the current. We also know the time, so we can find the rate. If we leave the tip long enough, this chlorophyll will switch back and forth. We can build a little molecule switch. We can change the average frequency by changing the current. We can also measure the energy required to rotate by simply changing the bias voltage. In this case, this is about 0.6 electron volt, then this rotation happens. If you do the statistics as a function of time and the number of events, you will see this kind of a statistical distribution, which always show exponential decay, because these are the physical events. So they always go exponential decay. From that, we can also calculate, determine the time. And if we choose the different times, then we can actually plot the rate as a function of current. The slope tells us the number of electrons that we use the process, and so on. So we can get many different physical information, and all of them are quantum processes at this level. So this is an example of that electron-induced conformation change, dancing of little chlorophyll molecule. Final one I want to explain is electric field induced manipulation. Because we use the STM tip, there is electric field. We apply the bias. If we apply the bias, normally won't happen anything on the molecule. But the molecule is the polar. There is a negative or positive net charges in the molecule. Then we can manipulate this just by applying an electric field. The same polarity, there will be Coulomb interactions. Coulomb repulsion will push the molecule or pull the molecule depending on the polarity. And that event happen, we can also measure by ramping the current and the voltage. If we change the bias, certain point, you see that the current suddenly drops because this car move away, this molecule move away. So we can determine the threshold bias required to move the molecule. So I'm going to use these three techniques to explore the molecular machines. Okay, so now I use the language I, but I have to remind that most of all, or almost all of these works were done by my students, and I supervised them. I'm going to show at the end their pictures. So we can actually reach the system. Let's talk about the molecular machines. So what are the molecular machines? So here it is, I borrowed from the web, these little machines at the top. This is not a molecular machine. This is a 50 micrometer. It's a huge machine. The right side is an Indian student from Japan. It's a cartoon, but it's an inspiration. It's to build the molecules by the machine. And here is a little nano car, a nano wheel. It's rolling off the process. But the molecular machine research was, in fact, given a Nobel Prize in 2016. And these were the Nobel laureates in chemistry. Most of the molecular machine nowadays concerns with large systems. I call it classical molecular machines because they are the size of the micrometer, like biological machines, for example, biological molecular machines. In our body, we have many molecular machines functioning. Those are in a micrometer sizes. So those systems follow the classical mechanics. Okay, so that's easier. But if we are building the machines with the molecules in the sizes of a few nanometer, then it becomes in quantum regime. That's why I call it the quantum molecular machines. There is an entirely different concept that we need to think. We all understand the quantum mechanics, but there is no quantum mechanical engineering. And when we start discuss about the machines, it's a little puzzle at the beginning, and we have to think through because the processes are not familiar. We cannot directly copy our macroscopic machine concept to the microscopic or in nanoscopic machine. And the topic that I'm going to discuss is also to operate the machines on materials surfaces. The goal is to incorporate the molecular machines into the solid state devices. So it's different from many biological machines which operate under the liquid or in ambient condition. So this small subset of the research area has been growing. It was started with some of the papers in the past with little molecular motors, molecular wheel, and molecular car. And in the last reference is, of course, this is the Nobel Prize winning molecular car here. Okay. In this case, the wheel rotates, but different way. It's just like a pedal. So the topic I'm going to talk, the first part of the projects is called Action Projects. It's a cross-Atlantic collaboration between my group at Ohio and Christian Joachim group is a theorist, and Guinea Ripan from Department of Chemistry at University of Toulouse. So the Guinea synthesized the molecules, Christian did some calculations, and we did all the experiments and we worked together. So let me start with the first part of little molecular motors, and I will move on step by step what we learned. In this part, we developed a molecular motor, but it is like the real molecular motor, real motor. What I mean the real is that it has multiple components. So we designed a system, it has a tripod. The tripod looks like a tripod, and it is a tripod. Okay, and it has 3 sulfur atoms, which is a sulfur ED groups. The sulfur atoms are designed as a glue to stick on a gold substrate. We can change that to stick on the silicon. For example, if we are to do it on silicon, this will be the oxygen. And here we use a sulfur atom to stick on the glue. And this, we call it the tripod stator. Here is our rotor. The rotor has 5 arms. Number 5 arms, the 5th one, we cut it off half by purpose so that we know when this one rotates, we know that the molecules rotate. Now think about this. We have the rotating part, we have a stationary part. we need to link them. If you want to link these two, you need a ball bearing. We use single atom ball bearing in the ruthenium atom so that if we put it together, the molecular motor will be looks like this. The top part will rotate, the bottom tripod will stick to the goal and always stay upright, not reverse. And when we put these molecules on gold 111 substrate and we took the images around 80 Kelvin, we already see that the molecules are rotating. You can see here it appears like round shape. I always jokingly call it's like a Mexican hat. The structures, because they are rotating. And this is 80 Kelvin. It's pretty low temperature, but the thermal energy is enough to make them the spin. So we need to go to the much lower temperature in liquid helium. To 5 Kelvin, if we cool it down, this rotating molecular motor stop rotating. Now we can see the 5 lobe structures. We can directly identify them. Loop number 1, 2, 3, 4, and 5 arms of the rotor. Now we took the image from the top, so we don't know whether the tripod is still underneath. This is the big molecule. And in order to confirm that, we increase the bias during imaging in order to blow up the top part. And when it reached to the negative 2.3 volt, we can blow up and you can now see the tripod underneath. With that, we give this absorption size back to the theorists, and this is the calculated structures except the shadow. And now you see that our little beast, this molecular motor, is 1 nanometer tall and 2 nanometer wide. Okay, now we know that molecules, the molecular motor. Now we want to understand its processes. I have explained before, this is in a quantum regime, so the rotation is quantized. If we are talking about the classical, it's with the thermal motion, it's a continuous rotation. In quantum, these molecules, these molecular motors rotate stepwise. So what we are going to do, we are going to inject the tunneling electrons to make stepwise rotation at 5 Kelvin, because at 5 Kelvin, molecules cannot rotate themselves by thermal energy. They are frozen. So here is the STM image of a molecular motor. And the background, the lines are gold 111 Harriman reconstructions we use as a landmark. We took the image, then we position the STM tip, inject the electrons. At the same time, we record the current at the fixed position against the time. We stay the tip there, and then we are recording the current. And at the same time, we are injecting the current. As you see that the currents, nothing happened, and then suddenly some change and go back, and then it drops, go much higher, and so on. After that, we took the image. Now we see that molecule has been rotated. And from here, based on the position I color-coded, from that, we know actually how the molecule was rotating as well. From that, we also know the time to transfer the rotational event. So we can make a statistics. So here is like over 100 rotational events. We see that it drops in an exponential decay. If we change the current, we change the number of electrons passing through the molecule. So we change the rate. That is in the form of different exponential decay. You can see the different slopes. Now, from 4 different points, 4 different time scale, we can plot this plot. In the Y, we have logarithmic ln rate. Okay, that's the opposite of the time. It's a 1 over time. And in x-axis is a log current. As this equation, if you put logarithmic r, logarithmic I, then you can take the ratio, the slope will be n. Here, the slope is about 1, 0.98. So we are using single tunneling electron energy transfer to make stepwise rotation. Now, the interesting thing here is that if we inject the electrons in the truncated one, I show here with the green, molecule rotate the clockwise direction. If we inject one of the 4 good ions, molecule rotate the counterclockwise direction, opposite. And we can control that. For example, if we rotate this to clockwise, more, and coming backward again, and so on, it turns out that we can actually control whether to rotate left or right, or clockwise or counterclockwise. And here it is the previous sequence. We have done many sequences and corresponding the theory STM images. Now we can control the direction of the rotation. We need to explain it, the physics, why this happened. Let's consider that we have 5 arms, 5 good arms, and we have 3 legs. If we rotate this 360 degrees, there will be 15 potential wells. Why 15? Because 5 multiplied by 3 will be 15. So 360 degrees divided by 15 will give you 24 degree steps. So this molecular motor will rotate in a step-by-step manner, each step 24-degree angle. If we carefully look at this potential, you will immediately notice that they are not symmetric. They are more like a sawtooth. Sawtooth has very important properties. Sawtooth potential. So if we have a state here, if we want to excite, it has a 50-50 chances probability to go either to the left or to the right. If the state is moved to the right, it ends up in the next potential well. That means it rotates. If go to the left, it reaches back the same place. It means it doesn't rotate. So if we have a sawtooth, we have a directional rotation only to the one direction. Because we cut the one arm at halfway, now it still has a sawtooth. This is the calculated potential, 15 potential wells, but it's no longer symmetric, but still maintain sawtooth potential. And excited state also has a sawtooth potential, but opposite direction. It turns out that the ground state 1 is corresponding to the location of the truncated arm, the cut one, while the upper one are location of the complete arms. So when we are injecting the electrons, we are injecting to the either with the, depending on the position, we can selectively excite one well or the other. That is the explanation that it makes directional rotation. So here is the movie. This is very expensive movie because we calculated like 0.01 degree step with the density function of theory in order to understand the mechanics during the rotation. You will notice that there are a lot of movement. Here is a truncated arm passing over to one of the legs. And they are not necessarily free. That's the reason the potential wells appear not symmetric, okay? So this is something that interests us. What happened? Can we learn during a rotation, these legs or the arms movement, can we directly detect with the STM? That will lead to this next project, chiral molecular propellers, published in 2019. Here, I'm going to show you how we detect detailed mechanical movement of the molecular propeller, we call it, during a rotation. We choose here the system, also the ruthenium atom as a ball bearing. We have 5 bromophenyl group as a stator, stick to the goal. We have 3 blades rotating. That's what we call it the propeller. And its shape appears when we deposit on gold, it appears like that, gold 111, Herringbone reconstruction. You see that these tri-plate structures are molecular propellers. If you look at close-up, it should appear like this in a drawing, but STM images show similar, but like this. So, okay, so that's a propeller. And some of the propellers here I show with a blue arrow are already rotating at 80 Kelvin. Close-up image appear like that. So this is already rotating. So we know that it works. And when we carefully analyze, we realize that they are chiral. So here I show with the white and the blue, they are in mirror symmetry. Okay, so these are. So the question is following. Is chiral rotate into the certain direction? Looking at that, I will say the left one will rotate clockwise. The right one, the blue one, will rotate counterclockwise. But is that true? And the second thing is that can we determine mechanics during the rotation process? And we can do both. Okay, so this is the chiral molecular propeller. So this is a calculated structure of the charge density plot of our molecular propeller. And here, what you see is the 5 bromophenyl groups are tilted one direction after absorption on the surface. In the gas phase, they are not tilted. They are in a vertical, the pine rings are. But here is a tilted. Depending on the left tilt and the right tilt, they form like a gear. Okay, it's like that. It's like a gear, and it will go only one direction or the other direction because the gear tooth will prevent this to rotate the opposite direction. And we have this red dot is a ruthenium atom, and these three are the plates. And I show here for this particular one, rotation direction is shown here. So the other chiral has an opposite of this, flipping the other side. Okay. Okay, so now first thing that we measure here is we use the electric field. So we position the STM tip, apply the electric field, and during the process, we also ramp the bias. So bias increases from 0 to negative bias in this case. Around negative 2.6 or 7, sudden change appear in the current, and we know that molecule has been rotated. And we took the image, it shows that molecule has been rotated. And we use this electric field manipulation to determine the critical electric field for rotation and the energy required to rotate. To do that, we change the tip height, and each tip height we measure by like a previous case, we measure the critical electric field for the rotation. So these are plotted here. And x-axis I show here are the relative tip height. So when the tip height increase, that means it's becoming far away. We need larger and larger bias, of course. And this is the negative, okay? So larger bias, we're going down. And if we plot it, we get a linear plot. The slope will give us threshold electric field required for the rotation. That is 0.25 volt per angstrom. Second, we want to learn about the mechanics. Can we directly detect what happened during the rotation? So we use the STM tip like atom manipulation this time, not electrons or electric field. We mechanically push one of the plates and we record the tip height signature in that process. So here is the molecular propeller, and we can rotate the same way by mechanical pushing. During the process, we have recorded the tip height. Here's an example. What we find here is very interesting. If we look at each curve, they look a lot of noise they have, however, there are similarities. I show with the red arrow, those areas appear little hole, just deeper. And then there is a pretty high rise in the tip height, shown with the black arrows. Then it has a sudden or rapid drop, and continue. This we can explain following. So when we approach the tip to the one of the blades, that's number one, and the tip is very close, somehow the blades move away from the tip before it touches. So the tip height drops because in STM, height is depending on the current. So the blades move away, it doesn't get the current, the tip drops. But blades cannot move farther because it gets stuck with the pine ring underneath. In that case, stopped. Now the tip reach to the blades and start climbing up here. Start pushing this. At number 4, the blade rotates to the next side, so it's pushed down. So this measurement shows that there is an internal movement before making the real rotation. And we check that by calculations. We find that these blades can rotate within that range of the, within that angle range between the two phenyl rings, although some of the phenyl rings are slightly affected by this flipping, swinging of the blades. So at final, I want to show that now we apply the electric field. What you are seeing is two motors are rotating clockwise and counterclockwise according to their chirality. Now I'm moving on to the last part of molecular motor. If we want to use the molecular motor for the applications, next thing that we need to consider is not one, but the interest is we want to use many of these molecular motor simultaneously. So we want to form thin film of molecular motors. Let's put it that way. So, and in order to operate, they need to communicate each other so that one knows that the other one is rotating. So we decided to add a communication channel between the molecular motors, and so that they can interact each other. Here, that communication channel is done in a way of dipole interaction. We have molecular motors which are lining up, and it has to have a dipoles. So here's the design. We have a stator that is the one to stick on the substrate. It has 4 legs. We have ball bearing, that's a Europium atom. And we have a rotor blades. Now we have only 2 blades in this rotor. And it has the internal charge transfer so that they have a dipole in between these 2 plates. And with large dipole of 8 dpi. We deposited these molecular motors on gold 111, but they are already rotating even at a 5 Kelvin. So we cannot work on gold 111. So we deposited on copper 111. On copper 111, we can form self-assembled network of the molecular motors. We can form hexagonal network like shown here, and we can form a parallel network. I will not show the parallel network today. Now the hexagonal network, what happened is that when you are seeing here the 2 lobes are in fact, those are the 2 blades of the top part of the molecular motor. We cannot image the lower part because we are taking the images from the above. Here is the theory calculated the STM image of the molecular motor. What you see here is the calculation shows that we should see as the 2 lobes, one side is a little bigger than the other. And they are actually coming from the top part of the rotor from the benzene ring, which is tilted. And if you see the big one and the small one, the dipole direction is from the bigger one to the smaller one. So arrow should be like this. So we took the images, again, this is the real STM image, not the drawing. I just put the color contrast to show the high contrast. You will immediately notice that the top part of the rotor shown here, one side is bigger. That's why it appears brighter. or here is a dark blue color. And the other side. So we know the dipole will be this direction. And if you look at them, you immediately notice that they are all pointing to the same direction. So we have a unidirectional dipole orientation in this self-assembled molecular model film. So they are ferroelectric system. Also, they have a hexagonal symmetry of the dipoles. Now we have a very interesting stuff to explore. So let's see what happened. So we took the images again, now at 80 Kelvin. And when we use the high biases, in this case, it's negative 2.3 volt to take the image, something happened as here's a line. Typically, one would think that, oh, there's a tip change. In fact, this is not a tip change. It's a change in the molecule. So in this area, something happened. If we put it the arrows, we immediately notice that the upper part I show with the green and the lower part I show with the blue has 10-degree angle difference. So they appear to be 10-degree rotated. And here we have a defect, and I will come back about the defect later. It's very, very important to have a defect. And we don't see this kind of rotation if there is no defect. Now, I'm going to show in a large area. Here we have the dipole pointing up, all of them. This is the defect site. In the next image, after scanning with the high bias, 1 volt, you see that in the right side has rotated the whole region. The left area remained the same. In between, a domain has been formed. And we have a slight rotational angle here also. So this is becoming interesting. Can we induce this with the STM manipulation? We can do that. Here is the STM image, a close-up. These are the plates of the molecular model. And here is a defect I'm going to use as a landmark. We position the STM tip, apply the electric field, and then take the image. During the process, we also recorded the current voltage characteristic. It shows a change at 1 volt. So we know that 1 volt is more or less a threshold voltage. And we saw they all rotated. I will just repeat this. This is the initial as the left image. After that is the right image. Defect is showed with the circle as a landmark. So they all rotated clockwise direction, and it got stuck with the defect. So we can induce that. To understand it, I have written down this Hamiltonian system. So here, the kinetic energy, because we consider as a quantized, and we have a dipolar energy term, we have electric field energy, and then we have a structural and thermal energy. Structural and thermal energy, because the world rotate, we assume that they are small enough for this energy range. And it turns out that the kinetic energy in a quantum is only micro electron volt, so extremely small. So we can totally neglect this. So in order to understand the mechanical process, we have to understand dipolar energy, that's a resistive, okay? It resists rotation. Electrical energy, that is the one that provides the energy to rotate. These two terms we need to analyze carefully. So first we look at it, because we have never been able to rotate one motor. They rotate all at once. Why? If you look at this hexagonal network, and if I want to rotate the one at the center, if you rotate, as soon as it rotates, energy increases. And when it's reached to the opposite direction, energy becomes maximum at 180 degrees. And it drops back after that. So you have an energy cost to pay if you rotate only one rotor. What happens if we rotate all of them at once? If we rotate all of them at once, it turns out that they all cancel out, and total dipolar energy, the net energy change is 0. That means if all the dipole rotates, it doesn't cost any energy in the dipolar energy portion. So that's the preferential reason that they want to rotate all at once. Okay, so my explanation seems to be good, but there is one problem remaining. That is the torque. So we apply the electric field to rotate, but we are applying electric field from a single point source called the tip. And the tip electric field emanates into the hexagonal lattice uniformly. So the problem is, if there is a torque, there already has an anti-torque. So if we want to rotate, we apply the electric field. That means that we are exerting a torque. But every torque will be anti-torque in the hexagonal network. So they will cancel out. So you can't have a net torque. You can't rotate. But if we create a defect, then we have a net torque because it's no longer able to cancel. So that's the reason that we need defects to rotate. And also, if you look at the torque, it follows 1 over R. Dipole 1 over R cubed. So dipole energy dropped very fast while the torque remained. So after the first nearest neighbor or second nearest neighbor, the rest no longer remember there is a defect, but they have experienced the torque. That's the reason that they can be forced to rotate. But the one near the defect may not necessarily rotate easily. Okay. Now I'm going to show you, this is a very large area. Every little one arrow is a one molecular motor. They are self-assembled in hexagonal network. The left side is a step. The right side is a step. The steps are also one-dimensional defects. Please remember. And we have a zero-dimensional defects here and here. And we scan this same area with the high bias and took the second image. Now you see that this area we have already rotated. The others remain. So this area is remaining the same. And here we have, this was previously shown, this part. But here we have a domain, but there's a frustrated, the dipole, the motors, they are switching between the two. That's why it appears as a crisscross. In the next scan, also we have rotated this part as well. But near the steps, it's difficult to rotate because the steps are defects. So we can rotate up to 500 rotors, can be switched collectively by increasing the defects. All right, so now I will go my last part, that is the linear vehicle or in the nano car. And let me start with the world first nano car race. It was in 2017. And this is our car, and we competed. We were one of the 6 teams, German, French, the Austrian and the Rice University team, Swiss, and that is our Ohio team, and the Japanese team. And we had nice cover in CNN News. They came to interview us in our lab at Ohio. And so the idea of this was with my colleague at Eric Mason. He is from OU Chemistry. He specialized the molecule called cucurbiturils. It has a pumpkin shape, so we call it the pumpkin molecule. Okay, so it's a time of hollowing, so pumpkin molecule. So the idea was that I discussed with him to use this molecule as a wheel, and then to create a nano car, looks like a real car, and it has a positive charges, so that we can use electric energy to drive. The rule of the race was that we cannot push the car with the tip. We have to use either electrons or electrical energy. So we designed that and synthesized these cars. It appears that these are the H frame, and the wheel are slot in. It's not chemically bonded. They just slot in by Coulomb interactions, electrical potential. And we did calculations. We were not sure that this molecule, the center ring can be stationary on the surface. So we did these very expensive calculations because this molecule has more than 700 atoms and on gold 111 surface. And calculation shows that they are stable. And it also shows that these rings are not chemically bonded and they are free. So this will be, the wheel may be rotating. And if we analyze this structure from the calculations, we see that we have a charge points which give a positive charges. So that's what we want to use to propel the car. So we deposited these the nano cars on gold 111 substrate and again took the image. Like a molecular motor case, at 80 Kelvin, these cars are already mobile. And you see here, these streaks are because these cars are moving. We can see here one car with the 4 wheels. We can image because this car gets stuck with a defect, it has an accident. And so this car. Here in this one, it's just moving down. So we capture only part of it. This is not the whole car. This is just only the end part of the car. It's gone here before we get its vertical position. Before we get the whole image, it's gone. And we can take the images only these cars, the wheel is broken. So here, for example, we have 3 wheels. The 4th wheel is broken here. So this car can't move. Then we get the image. We can even take the image of the wheel. We can see it looks like a wheel. So how do we move that? So we use the STM tip. We have a positive charges in the molecule. So if we apply the positive bias, it will be pushed. And we also measure the energy to move the car, and it's about 800 millielectron volt. So here is the snapshots from the Nano Car Race. We have our car here, 4-wheel, and we move. We're driving and we turn the car. We're driving down and so on. And this was cross-Atlantic molecular manipulation. This was the first ever cross-Atlantic molecular manipulation. Among the 6 teams, the 4 teams use a 4-probe STM locally in Toulouse in France. The Austrian team use their STM in Austria, but they have the same time zone. We use our STM at Ohio University and we manipulated the molecules from France. So it's the first cross-Atlantic molecular manipulation. And at that time was pre-pandemic, so people don't used to manipulate that far, but we did it. But we were not lucky enough. During the race, we got the rain came. There was a power outage, and we lost our car. We did not finish, but we still got the 3rd prize. Yeah, it's not bad. And we won the Texans prize for the largest nano car in the race. Now, the 2nd race is coming, Nano Car Race 2. Initially, the race would have been in this year, but we postponed it because of the COVID. It will be the next year. This time, we are competing with the gigantic 2-wheel vehicle with a double deck axle. And these wheels are much bigger than the previous wheel. And we plan to run and faster. And we have tested this in our lab in the previous case. In that case, we have a 2-wheel. This is not the same car as the one I just showed, but an example that I want to show that this a little bit smaller wheels, how it works. And so here is the little movie. What you are seeing here is a 2-wheel. This little green dot is the one that we position the tip, and we use the positive electric field because it has a positive charges to push. And you will see that the wheel move same time. Sometimes it's captured by the defect or the steps potential. We have to try to remove. the car out of those traps. We are not allowed to push with the tip. So we just use the pulses from the electric field. And you will see in the movie. Now we are trying to remove the car from the trap of that solid and the step. Okay, so the next one is the same thing, but now this time we are using the negative bias to move. But based on the time, I will skip that. So finally, we are now almost ready for the Nano Car Race 2. And preparations are underway, and that will be in March 2022. And this also will be live broadcast online. We will have also dedicated website, and I hope that you will support us in that game. So let me summarize today's talk. I have presented first a molecular motor, and then I presented chiral molecular propellers, then molecular machine networks, finally supramolecular nanocar. Here are the supported fundings, and most important group of people who actually did the work were my students, my current students, the Michael Charles, they were instrumental in molecular propeller. So Myo-Win was instrumental in that little nanocar movement. And Sanjoy and Josin Luck were the ones who helped prepare all the molecular cars in the previous race, and they were staying in the lab day and night when I was moving the cars, driving the car together with my former undergrad students, Ryan, and all the other members contributed in different parts of molecular machines. And finally, I want to show you with this little smiley, and thank you for your attention. And if you have questions, please.
Thank you so much. For this smiling face at the end and for all the talk. Now we are open for questions. If you want to, David, please, you have raise your hand.
Thank you. So thanks a lot, Sal, for a really nice presentation. Especially appreciate the animations; they make it way better. So I have two small questions. So one has to do with the hexagonal lattice system that you were showing. So the two bladed rotors. So I couldn't help but notice that you have essentially almost a textbook example of a statistical mechanics problem, like something like an XY model in a triangular lattice. So I was wondering if you could, for example, try to do something with temperature and start measuring susceptibilities, taking snapshots with the STM and try to get susceptibilities, something like that, like try to simulate this textbook example.
So in fact, we plan to continue to study. We didn't get the chance to do. We found very interesting things when we changed the temperatures. Honestly, we do not understand, so we realized that there are a lot of things happening there. And I discussed at that time with my grad student. Now she is a professor in Old Dominion University, Yuan Zhang. And we discussed about that, and we decided that we should continue exploring. And that was that. We still haven't done that a proper analysis with the temperature, because there are a lot of very, very strange things happening. And I know that there are a lot of interesting things, physics out there. So we plan to do it, but we haven't yet. Yes, that's the answer.
Okay, thanks. And the other question that I was going to ask was whether you have considered exploring coupled systems. So you have a rotor maybe somehow coupled to another rotor, you know, two molecules interacting one with another.
Right. So we have tried to couple. That coupling is becoming not that easy, and we are working on that. The reason is that when we consider like initially we consider it's like a gear. If you want to put together, you rotate one and the other one rotate and so on, cascading the rotation, but they do not have mass. Their interaction is not like the classical gears. The interaction is more of the Coulomb interactions or steric repulsion. And so that if you try to rotate one, the second one gets stuck and so on. It's not easy, we realize. And we are still working on that because we have tried to couple a number of the motor, and it's, as I said, it's not easy as we expect. We can assemble, but excuse me, we can assemble the lines, but we want to try to rotate one to rotate the second. That is not that easy.
I see. Well,
Okay.
thanks so much.
Thanks. We have a question from YouTube from Ernesto Alba. First, he says, thanks a lot for the great talk. And the question is, do you know any nanoscale system that works as a machine but made up by atoms?
Made of the atoms?
Uh-huh.
And working as a machine? No. So okay. The group of atoms, right? Molecules are the group of atoms. It functions. But if you use one atom, I don't know how to build a machine with one atom. You need something else to be considered as a machine, right? In order to function as a machine, you are either rotating, at least the simplest form. You have a rotating part, you have a linear or parts, you have moving parts. Those are we consider as a machine or machine parts. For the real complicated machines, you should combine all of these things to make a useful things, right? So we are at the very, very beginning trying to understand how things are working in this scale. So it's way behind even compared to the micro, because most of the micromolecular machines already exist in the nature. These nano machines are something which is much more complicated, but atoms, I don't know any specific example with one atom, for example.
Sure. Okay. I don't know if there is another question or not. Yes, Adolfo Cordero, please.
Yes, thank you very much. It was a quite nice talk from my point of view. Thank you very much. And I would like to make just two simple questions. The first one is, why did you use Europium atom as a bearing ball mechanism in one of your models?
You mean why do we use the Europium?
Yeah.
Simply because of the coordination.
Right.
So you can choose other rare earth atoms easily. Also the ruthenium is the same reason.
Okay.
So it doesn't have to be Europium. But Europium has, of course, it has additional properties which is related to the bigger. It's a rare earth. It has 4F elements and may have an interesting spintronics behaviors. But the one that we measure in particular, the one that we have measured is neutral.
Okay, thank you very much. And my other question is, how fast was the race? I mean, the first, the winner, how fast achieved to move the machine?
So the race in a fast is very artificial.
Right?
Let me explain this way. The movement between the step, again, it's a quantum. So if you excite one step, it moves to the next. I will assume that in a typical range of the gigahertz, that again, it will be in a nanoseconds approximately. Now, why I'm saying the artificial? So we have to take the image with the STM tip, which is pretty slow, range typically in milliseconds at the data points, and the scanning takes like a minute. So you have the image, you move, and then you have a second image. The taking image takes like a minute or several minutes. Actual movement time is like in nanoseconds. It had just flipped it, just already there. So in fact, you can calculate the speed just by the mass of the molecule without even erasing it. So if you have a bigger mass, it will be slower.
Yes.
Right? And you can already estimate from that. But the real race that we are talking about is just for fun, just to make the scientific outreach to the public. And that is our goal. And so that all depends on who get more practice with the STM. So it's a little more artificial.
Okay. Yes. Thank you very much.
Thank you.
Thank you very much for your answers.
Okay. I don't know if someone else has a question. I have probably a couple of questions. So, for example, when you have these chiral propellers, you have these three arms, no, in some way, and the end of the arms have a different orientation that gives you the chirality of the system.
Yes.
And the propellers move more like you are injecting, no, the electrons in some way, and then you have the movement in some direction or the other one. But at the end, you have a threefold or something symmetry, except for this last part of the arms. And how is the real mechanism to move in one direction or the other, just because of this? Because what I mean is that only one small part of the molecule is the one that gives you the chirality of the system,
okay, so
no? Which is geometrical.
Right. It's based on the the direction of the teeth.
Okay. So you can give.
So here, for example, you see that we have 5 rings. It's formed like a gear. So in this case, the rotation is this because it's easier to pass. If you go opposite, now this guy will get stuck with this step. It likes here. So in this case, you will go, it still has to climb up this, and then it goes down the step, and so on. So if you want to rotate in this direction, it's easier. If you want to against it, now this will get stuck with the step.
Okay.
So the left and right chiral are formed due to left and right tilting of these spine rings.
Okay.
Now here it is all tilted to like to the right side. You can have another 50% chance to have opposite tilting, not like this, but that opposite tilting. Then this guy will rotate the opposite direction.
Okay.
Okay. So chirality is induced because of the gear, but gear is the one that detects which direction to move.
Okay.
So this is more robust in a sense that if you can excite, it should follow gear. Where the previous direction that I show with the injection is now you have to use the STM tip to find the location to inject in order to control.
Right.
This one, the gear itself is controlling where to go.
there is an experiment where using the tip, the people can give some chirality to the
Yes, there was an experiment from the Tufts University.
And
Professor Charlie Sykes group. Right.
And
we haven't tried that. Yeah.
Okay.
They use the chiral tip, and they explain that because of the chirality of the tip, somehow that induces the
kind of momentum or something.
Something, yes. But our system is different. This is the chirality is directly related to the
to the geometrical.
Right, geometrical. It's like forming the real gear like thing. So this has to follow that. It doesn't matter how you excite. This has to follow this. That's the point.
Okay. And for example, for the car, in some way, in some cases, you have these sulfur atoms that can attach to the system.
Yes.
Some way, and then you move some other parts. And for the car, you use molecules that are not attached to the system, no?
Yes, yes. Because we want to move. Here, we don't want to move. We don't want the motor is moving around. We want this to rotate. It sticks to the goal. The other one, we want that it is mobile because it is for the car, the transport.
Right.
This one is we need to fix. What?
So what kind of interaction you have, for example, for the wheels and the substrate? Do you have a different kind of, in order to have a way to stay in order, or the thermal interaction also plays a role there, or not?
It's a van der Waals interaction. Excuse me.
No, it's okay.
It's a van der Waals interaction. The wheel to slot in, it's a Coulomb interactions, of course. It's electrostatic interactions because the wheel inside is negative, and you have the axle which has a positive charge. It wants to go inside, and so there is that interaction in the wheel. But the movement of the process is just simply the thermal, and on the surface is simply it's the van der Waals interactions, I think.
Okay.
Sorry, not this.
Yeah, well, the thermal will be in any direction, and the other one you can move in one direction.
Right.
No?
So here, for example, sorry, this is the side view, and I got a cold with this weather. So you can see that the wheel is not physically attached. You may not notice here because of the angle. In fact, it is not physically attached. It is free. And because it is free, and then why they are staying together? Inside, there is a negative potential of this wheel, and this one has a positive. So there is attraction, and it balances, they stay at the center. So that is a very unique circumstance, I will say. So it's very different from the other cars, which they use like chemical bonding and rotation of the bond, so on. Here has no bonding. It's a supramolecular car because it has 5 separate molecules. It assembled separately, and then they just slot in to form a single car.
Okay. I don't know if someone else has a question. We can translate if you can. You want to write something in Spanish. Si quieren hacerla en español y podemos hacer la pregunta. Well, if not, well, thank you so much. So
well, thank you.
I have seen a lot of people that has been in Ohio here in the audience. Okay, Sergio is here, Lilia, and so many other people around. Thank you for all of you.
I
Thank
have
you.
invited some of them.
No, thank you for being here and give us this interesting talk.
Thank you for the invitation.
And you do be very, very, very nice work
Thank
with
you.
all these devices. Thank you so
Bye-bye.
much. Take care and see you.
Yeah.
Gracias a todos. Cuídense mucho. Que estén muy bien. Hasta luego.
Hasta luego.